So, have you ever thought about the hidden language of triangles? It turns out they're these super simple but really powerful rules that connect the length of a triangle's sides to the size of its angles. And once you see them, you're going to look at triangles in a completely different way.
All right, take a look at this triangle right here. Without grabbing a ruler, how can you be absolutely 100% sure which side is the longest? I know, it feels like a trick question, right? But stick with me, and by the end of this, you'll be able to answer that in a heartbeat.
So here's how we're going to break it all down. We'll start with a simple rule of balance. Then we'll build on that to really get the relationship between sides and angles. After that, we'll level up and start comparing two triangles at once. And finally, we'll put it all together and you'll be a triangle master.
Okay, first things first. We need a starting point, a baseline. To understand what it means for things to be unequal, we first have to know what perfect equality looks like. And that's why this entire journey begins with the simple, symmetrical isosceles triangle.
See, an isosceles triangle is all about balance. If you've got two sides that are exactly the same length, then the angles sitting directly across from them, they're also going to be perfectly equal. This is our foundation, or rule number one. Equal sides mean equal opposite angles. Now lock that in, because we're about to start breaking that perfect balance.
So, what happens when we do unbalanced things? What happens when the sides aren't equal? Let's jump into our next building block and see how that completely changes the game.
And this right here is the absolute key. When one side of a triangle is longer than another, the angle opposite that longer side is always bigger. You can think of it like an alligator's mouth. The longer side represents a wider opening, a bigger gap between its jaws, and that creates a bigger angle.
This picture makes it totally clear. Side AC is obviously longer than side AB. And look, just like the rule says, the angle across from that longer side, angle B, is bigger than angle C. It's a direct, predictable relationship. Simple as that.
Okay, your turn. Quick challenge. Say you have a triangle with sides of 25, 17, and 15 centimeters. Which angle has to be the largest one? Just think back to that alligator rule we just talked about.
You got it. The 25-centimeter side is the longest one, so the angle sitting right across from it, angle C, has to be the biggest angle in the whole triangle. It's that easy. If you know the sides, you automatically know the size order of the angles.
Now here's where it gets really powerful. This whole relationship isn't just a one-way street. The logic works completely in reverse, and that gives us another amazing tool for our toolkit. This is what we call the converse. Basically, the rule works backwards too. If you know one angle is bigger than another, then you instantly know that the side opposite that bigger angle is the longer one. Let's go back to our alligator. If its mouth is open wider, meaning a bigger angle, then the distance between the tips of its jaws, that opposite side, has to be longer. Check out this example. Angle B is 70 degrees, way bigger than angle C at 50 degrees. So, what does that tell us? It means the side opposite angle B, that's side AC, must be longer than the side opposite angle C, which is side AB. It just has to be.
Okay, let's just see this side by side so it really sticks. On the left, if you know which side is bigger, you know which angle is bigger. And on the right, if you know which angle is bigger, you know which side is bigger. It's a perfect two-way relationship.
All right, so we've totally mastered how this works inside a single triangle. But what if we want to compare two different triangles? Well, this is where we really start to level up our skills. This next tool is called the hinge theorem, and trust me, it's super intuitive. Just picture two identical doors. If you open one door just a little bit and the other door really wide, which one has a bigger gap between the edge of the door and the wall? The wider one, right? Well, that's literally the hinge theorem.
And this right here shows you exactly how it works. We have two triangles, and notice they both have a 7-centimeter side and a 9-centimeter side. But the hinge angle between them is different. On the left, it's a wide 80 degrees. On the right, it's a smaller 50 degrees. So the hinge theorem tells us that the third side, the one opposite the bigger angle, BC, has to be longer than the side opposite the smaller angle, EF.
All right, team, we have collected all of our tools. We've got our whole toolkit ready. Now it's time to put it all to work and see how these simple rules let us solve problems that, at first glance, look way more complicated than they actually are. So, take a look at this challenge. The goal is to prove that the big angle down at the bottom, DCB, is greater than the big angle up at the top, DAB. It looks kind of messy, right? But don't worry, we can totally break this down with the rules we've just learned.
So here's how we tackle it. First, just look at the top triangle. Since side AD is longer than side DC, we know that angle 2 has to be bigger than angle 1. Easy enough. Now, look at the bottom triangle. Side AB is longer than side BC, so we know angle 4 is bigger than angle 3. All we have to do now is add the two bigger pieces together and the two smaller pieces together, and boom, we've proven it.
And you know, this toolkit isn't just for proofs. These rules are incredibly versatile. You can even combine them with a bit of algebra to solve for a whole range of possible values, which is super useful for all sorts of geometry problems.
So, let's do a quick recap of the awesome toolkit you've just put together. We started with the simple rule of balance. We learned that the longest side is always across from the biggest angle, and the biggest angle is always across from the longest side. We added the hinge theorem to compare different triangles, and we saw how to put all these ideas together to solve some pretty complex stuff.
And that leaves us with one last thought. You see triangles absolutely everywhere in the real world, in bridges, in buildings, in cranes. Now that you have this toolkit, how do you think engineers use these exact same rules about sides and angles to build structures that are strong enough to hold up our world? It's something to think about.